Can anyone tell me what section we're up to? Where we are on the syllabus? Well, I'll say a few words, answer a few problems. So if you watch the video, you know, if you have a function y equals f of x, and you graph it, a point like this is what is called a relative minimum of the function. Because in the neighborhood of this point, this is the lowest value the function assumes. This point would be a relative maximum. It's not the largest value the function is when you look at the graph, but in some neighborhood of that point, that is the largest value. On the other hand, if you have a finite interval, say this is x equal a, x equal b, and if you have a continuous function on this interval, so here we have the function f of x for x between a and b, it's a closed interval, and our function is continuous. This is a relative minimum. This is a relative maximum. But you see here, this point is actually has a lower value than this relative minimum. And this would be called the absolute or global minimum. This is a relative max, this is a relative max, but this one is bigger. And this point would be called an absolute or global maximum of the function on the interval. And to summarize what was in the lecture, on an open interval, for a function which is differentiable, if f of x has a relative minimum or a relative maximum at the point x equals c, then the derivative at c is 0. That's really the most important fact about relative minima and maxima. But the converse isn't true. So for example, consider the function f of x equals x cubed for x between -1 and +1. So the graph of the function looks like this. And if f of x is x cubed, f prime of x is 3x squared, f prime at 0 is 0. So the derivative at 0 is 0, but x equals 0 or c equals 0 is neither a relative max or a relative min. And of course, you can have relative extrema. Extrema means it's the plural of extremum. That means a minimum or a maximum, even if f prime of x, the derivative, does not exist. So it's a nice example. If you look at the function f of x equals the absolute value of x, the graph looks like that. X equals 0 is a relative minimum, but this function doesn't have a derivative at 0. So being differentiable is not a requirement to have a relative minimum or a relative maximum. So these points where the derivative is 0 are important because it's a necessary condition for a differentiable function to have a derivative equal to 0 at a relative minimum or a maximum. And what is called a critical number of the function f of x is number c, such that f prime of c is 0. Or, should I be very careful about this? A critical number is a number c where the function is differentiable and has derivative 0, or where f is not differentiable at c. So for example, if you look at the function f of x equals x squared, say x cubed, minus 4x, what are the critical numbers? So this function is differentiable everywhere. The derivative is 3x squared minus 4. That's equal to 0 if and only if 3x squared equals 4, x squared equals 4/3, or x is plus or minus the square root of 4/3. Those are the critical numbers. And in fact, if you were to graph this function, this is equal to 0 when x is 0, 2, or minus 2. And the graph of this function, let's see, what is square root of 4/3? That's plus or minus 2/3 times the square root of 3, I believe. This is about 1.7, 1.8. This is approximately 1.2. And the graph of this function looks like this. And here, this is the point minus root 4/3. That's a relative max. This is the point plus root 4 over 3. And that's a relative min. And a very important problem is to find the extrema, relative maxima, relative minima, absolute max, absolute minimum on an interval. So find the extrema of the function f of x equals 3x to the fourth minus 4x cubed on the interval from -1 to 2. So you have to find the critical numbers. If f of x is 3x fourth minus 4x cubed, f prime of x is 12x cubed minus 12x squared. That's 12x squared times x minus 1. And that's equal to 0 if and only if x equals 0 or x equal 1. So these are the critical numbers. And then we evaluate f of x at the critical numbers and the endpoints of the interval. Let's make a table x and f of x. The critical numbers are 0 and 1. The endpoints of the interval are -1 and 2. F of 0 is 0. F of 1 is -1. F of -1 is 7. F of 2, let's see, 2 to the fourth is 16 times 3 is 48, minus 32 is 16. So if we wanted to graph this function, on the interval from -1 to 2, at 0, it's 0. Let's make this 16. So this is 8. This is -8. At 1, it's -1. At -1, it's 7. At 2, it's 16. And the graph of the function looks something like this. And if you look at this, you see this is a relative minimum, and it's also the absolute minimum. That's the point 1 minus 1. And this point 216, that is the absolute maximum. Let me just say a few words about Rolle's theorem and the mean value theorem, because these are very important to understand. So suppose you have a function y equal to f of x, and there are 2 points A and B where f of A and f of B take on the same value. If the function is continuous on this interval and differentiable in the open interval, the graph has to start here and end up here. So it can do all sorts of things, but it has to start here and end up here. And the Rolle's theorem says the derivative is 0 for some number C, which is strictly between A and B. For example, at this point, that's such a number C. I mean, there are many such numbers, but Rolle's theorem says there's always at least one. And the mean value theorem generalizes this. See, one way to interpret Rolle's theorem is you have these two numbers A and B, and the line between them, the straight line between AF of A and BF of B, is horizontal, has slope 0. And there's some point between A and B where the derivative of the function is 0. So the generalization of that would be the following. Suppose we have the graph of a function, say from A to B, and we don't assume that the value at A equals the value at B. So we have AF of A and BF of B on the graph. They're not necessarily equal, those points. But for any 2 points in the plane, you can always draw a line between them. This is a chord. And what is the slope of the chord? It's rise over run. The rise from here to here is f of B minus f of A, and the distance from A to B is B minus A. So this number m is the slope of the chord of the straight line joining these 2 points. And the mean value theorem says there exists a C such that C is between A and B, and at that point C, the slope of the tangent is exactly the slope of this chord. In other words, there's always some point on the curve where the tangent line is parallel to this chord. And in fact, for example, at this point, the tangent line is parallel to the chord. It looks like there's another point over here where the tangent line is parallel to the chord. Again, the mean value theorem says there's always at least one, and there can be more. So this is the chord, or sometimes called the secant line. So just as an example of this, suppose we take the function f of x equals 5 minus 4 over x. What does the graph of this look like? It's not defined when x is 0. But as x goes to infinity, this is approaching y equal 5. That's a horizontal asymptote. Let's see. When x is equal to 1, it takes on the value 1. When f is equal to 4, it takes on the value 4. Let me draw a better picture of this. So it's 1 at 1. It's 4 at 4. When x is 2, it takes on the value 3. When x is 4/5, it takes on the value 0. The graph of this function for x greater than 0 is this sort of rectangular hyperbola. And I want to look at these 2 points, 1, 1, and 4, 4. So this is the secant line between them. And the slope of the secant is 1, because as you go from 1 to 4, the rise is 3, the run is 3. So the slope of the secant is 1. So the mean value theorem says, f prime of x equals 1 for some x. How do you find it? Well, what is f prime of x? You differentiate 5, you get 0, right? F of x is 5 minus 4 over x. So the derivative of 5 is 0, minus 4, the derivative of 1 over x is minus 1 over x squared. So the derivative is 4 over x squared. And that equals 1 if and only if x is plus or minus 2. So there's the value of 2 is between 1 and 4. This is the 0.22. And the tangent line there has slope 1. So by the mean value theorem, there's some point between 1 and 4 where the tangent to the curve is parallel to the secant line, has slope 1, and we just found it. Okay. All right, well, any questions about this? I'm not sure anyone is actually alive out there. If not, we've just covered sections 4.1 and 4.2, and we have office hours today, tomorrow, and Friday. So if you have questions about this or homework problems, I encourage you to log in and ask questions. If not, we're done for the morning. Bye all.